Hello, Sauce here. This is a lesson on more practice with instantaneous rate of change. IROC problems are very rich in calculation, very rich in concept, and there's a lot of different real-world situations where we would use this math. I have an equation, h of t is equal to negative 16t squared plus 80t plus 5. And we're going to imagine that this equation is for the height of an arrow t seconds after it's been fired. The arrow is going to have a parabolic trajectory. This function determines the height in that trajectory. So the arrow starts at an initial position, it's going to go up, and it's going to come down. One typical question we could ask in this situation, in this context, is what is the speed of the arrow after a certain amount of time, in this case, after 3 seconds. And we're going to state that the height is in feet. We have units for both of our variables. So we're given a position equation. Height is a position concept. It implies that it's a vertical position that we care about. And speed is related to velocity. Speed is the magnitude of velocity, or the absolute value of velocity. It means that at speed, we don't care whether we're going up or down, left or right. We don't care about the sign of the velocity. We're going to ignore the sign of the velocity at the very end of the problem. What's the relationship between velocity and position? From previous lessons, we know that position and velocity are related. That means that if we have information of one, we can use it to get the other. If we have position information, and we do with our height equation, vertical position, then we can get information about the speed or the velocity. And the tool that we use to do that is IROC. Velocity is the rate of change of position. Speed that we're trying to calculate is the rate of change of the height of the arrow. So we're going to do an IROC problem. And we're going to start, as is generally good to start these problems, with the general expression first. The general expression for IROC is the limit as h goes to 0 of the function at x plus h minus the function at x all over h. Notice that I'm using the symbol h in the IROC expression to be the horizontal change. That horizontal change is going to 0, and from previous lessons we know that that's how an average rate of change becomes an instantaneous rate of change. To have the distance between 2 points shrink to 0 so that it's the slope of a tangent line at a single point. And notice though that I've got an h being used to be the name of my function, which is natural because this function is for the height. It's determining the height of something, so h is a natural name for it. But I shouldn't be using the same symbol in 2 different ways in the same problem. It'll cause confusion. So I'm going to change the height function to be a capital H, different symbol. Capital H for the function, lowercase h in the IROC expression. Let's keep going. So in this general expression, I have f of x being my generic function, but in this problem, f of x is going to be capital H of t. And instead of the generic x, I have a specific domain value 3. I want to know the speed after 3 seconds, where time is equal to 3. I'm going to continue with this and write the general expression. The limit as h approaches 0 of capital H evaluated at 3 plus lowercase h minus the function evaluated at 3 all over lowercase h. Let's go another step further. The limit as h approaches 0. Now I'm going to compose, using the expression, I'm going to compose my IROC expression with the actual function. And this is going to be long. There's a lot of terms in there. Here we go. Negative 16, but where I see a t, I'm going to replace it or compose it with 3 plus h. 3 plus h all squared plus 80, and then I get t again, so I'm composing it with 3 plus h instead, plus 5. Now I need to subtract the function evaluated at my given value, in this case 3. Because there's several terms, I'm going to use parentheses because I'll be needing to distribute a negative. And that is going to be the function again, negative 16, but instead of t, it's 3 squared plus 80 times 3 plus 5. Close the parentheses all over h. There's a lot to keep track of in this numerator. We need the practice doing so. Next line. The limit as h approaches 0. And we've got to be careful and do one thing at a time. This negative 16 will distribute the expansion of 3 plus h all squared. 3 plus h all squared is 9, plus 3 h's and another 3 h's, 6h, and then plus h squared. I'm going to distribute this negative to the 3 and the h. Oop, 80 times 3 is 240, plus 80h. This plus 5. And then I'm going to be distributing the negative and evaluating some terms inside here. 3 times 2 is 9. Then times 16 makes it 144, but it's negative. And then when I distribute the negative to that negative 144, I get a positive 144. 3 times 80 is 240, which is positive, and then I make it negative from this distribution. This positive 5 then becomes negative after the distribution. All over h. Now there's some things that happen that are helpful. When we do the expansions, we can see that we're creating terms that we're going to be able to immediately cancel. The positive 240 there and the negative 240 can cancel right away. So can this positive 5 and this negative 5. They're gone from the problem. And when I distribute this negative 16, we're also going to create some things that are going to further help and reduce the numerator. Negative 16 times 9 is negative 144. Negative 16 times 6 is negative 96, h. And then we have a negative 16 h squared. Positive 80h is still around, and this positive 144 is still around, and we're still dividing by h. Okay, we have a positive 144 and a negative 144 that can immediately cancel. I have, in my next step, I'm going to do two things at once. I have this negative 96h, which combine with the 80h, which will make a negative 16h when I combine these terms. And then that negative 16h, I'm going to immediately divide by h here to get negative 16. So I combined these two terms and then divided by h. This negative 16h squared doesn't combine with anything, but it's also being divided by h. So we have a negative 16h remaining after we do the division. And finally, at this step, we no longer have a problem if we were to take the limit, because substituting in 0 now for h doesn't cause the division by 0 error. It will always be the case when you work an IROC problem that the division by h issue will algebraically resolve itself, and it's at that moment that we take the limit. We can't take the limit before. Taking the limit now means that I replace h with 0. This negative 16 doesn't have an h in it, but this other here, negative 16 times 0. And notice that this is the first time I didn't write the limit statement out front, because the limit has been taken. Cleaning it up, negative 16 minus 16 times 0 is the same thing as negative 16 minus 0, and what results is negative 16. We've evaluated the velocity, or the instantaneous rate of change, of our capital H function at 3. And the answer is negative 16. This is a contextual problem, so this is a speed. This is negative 16 feet per second as a velocity. The fact that this is negative means that this arrow in its trajectory after 3 seconds is going down. It's speeding downwards now. But the problem asked us to calculate the speed, not the velocity. So we have one last step to take. This is going to be equal to the magnitude of 16, or the absolute value, is 16, and include the limits. We want the positive value as the answer for our speed.